we're live. Welcome, folks. So today we're going to be talking about Hancitor, and specifically the Hancitor DLL, which is at the end of their delivery chain. So usually they have like a maldoc which executes some scripts and then it runs this DLL. So what we're going to do is we're going to reverse engineer that DLL today, and we're going to build a config extractor for it. I'm just going to wait. We're a little bit early, so I'm just going to wait a little bit for more people to jump on the stream. And I guess as we wait, I can give a little plug here to Brad over at Malware Traffic Analysis. You guys know we like grabbing samples from him, and he's done a nice write-up here where he's kind of explained the delivery chain. So this is like how Hancitor was delivered right from the mal spam all the way down to the actual DLL, which we're going to be analyzing. So that's basically where we grabbed our sample. Like always, in the description of the video below, we'll put some links for where to find this article. We'll put some links for the Unpacked Sample so you guys can follow along at home. And we'll also put a link for the lab notes, which we upload to GitHub. So in our lab notes, it's basically a Jupyter Python Jupyter Labs document, and what that allows you to do is allows you to both read like Markdown, sort of like a little blog article, but also copy out the code that we show in the stream here and use it yourself. So it's kind of a nice way to share the code that we're developing here with you guys. Hey, I see Duncan in the chat. Holy jeez, how's it going, Duncan? For those of you who don't know, he's a developer for X64 debug. Nice to have you on the stream here today. I don't know. I don't think we're going to be doing any debugging, though. I think we're going to do all this statically. So, but I did actually, for those of you who are interested in doing a little bit more deep dive into malware analysis than what we're showing here, I did unlock a video over the weekend on our Patreon. For those of you who don't know, we have a Patreon here. And you can go, and we unlocked a video here where we talk about how to debug DLL with X64 debug, and how to do it when the code you want to debug is in one of the exports of the DLL, so it's not in DLL main. So we just show you a little trick there that we can use to get that set up in X64 debug and sort of step through some debugging if you guys are interested. So we unlocked that for everyone. Yeah, X64 debug static win. Yeah. Yeah, Brave browser. Yeah, so I'm actually in my... Hey, it's Changdong. I think I mispronounced that, but hey, good to see you in the stream there, Chang. I like your additions to the Flare hash API hashing library. So I was recently looking at, I think it was Conti you added. I was looking at the Conti API hashing algorithm. So thanks for that. I like your blog articles as well. Okay, I think we are gonna reach enough people here. 12:07. Let's get started here. So, like I said, we're going to be talking about Hancitor. Hancitor, it's a loader that's been around forever. I think like 2014 or so. They've been operating, forever. They had a different name, like Chantor, I think, and there's another name too. I can't remember, like Tordel or something like that. Anyway, they've been around forever. And what we're going to do is we're going to look at the most recent version of their incarnation. You'll see a lot of these mal spam. Like a lot of their delivery starts with these mal spams where you have sort of a link in an email. You go and you download some sort of document, usually like in a zip file or something like that. They're trying to bypass AV, they're trying to bypass your detections. Once you download it, they ask you to like open it and you get a maldoc. You have to enable macros, of course. There's lots of like reliance on the user clicking through things for this to be delivered. So once you click on that, it's going to run some malicious code. And in the end, what it's going to do is it's going to drop and execute a DLL. And that's what we're going to be looking at today. And the DLL's purpose, just in general, is to call out to a C2, log the fact that they've infected a host, and then download some second stage payload. And recently we've seen a lot of payloads like Cobalt Strike being dropped. And I think I'm actually going to pull up, I saw a very nice article from the DFIR report here talking about what happens after the Cobalt Strike beacon has been dropped, and they talk a little bit about some of the lateral movement and discovery that's being done. If you guys hear that snoring, my bulldog is sleeping right beside me. I think he's having some deep dreams there. He's snoring. Anyway, so after the Cobalt Strike beacon is dropped from Hancitor, you see a bunch of lateral movement and stuff. If you guys are interested in this sort of deeper dives of what happens after the delivery stage of malware, definitely check out the DFIR report. Really awesome work from them. So for today, the sample that we use, like I said, is from Malware Traffic Analysis, and we just downloaded their artifacts here, downloaded the zip file, open it up. I'll just download it to the desktop here. And we grab this yef.dll, which is the Hancitor DLL. Now, this is actually packed, and of course, you guys know what's coming next, right? If we have a packed malware sample, well, what do we do with it? Well, we throw it into UNPACME, and we unpack this child here. And of course, we have the little Hancitor Yara match from Malpedia. Thanks, Malpedia. And so this is the sample that we're going to be analyzing. It's a DLL, and it has 2 exports here. So we're going to have to take a look at that in IDA. And of course, it wouldn't be a plug for UNPACME if we didn't play
UNPACME, a malware unpacking service from Open Analysis. Expose the malware before it exposes you.
I'm sorry. At some point, I'll stop playing that commercial. I just have to play it every time I say UNPACME. Okay, anyway, so we're looking at this sample here, and let's get it loaded up in IDA and take a look and see what's going on here. So I'll open up our IDA here. And I dropped it into my malware folder here to keep things nice and organized. Where's Hancitor? And so for today, like always, we're going to be using the IDA decompiler, just a paid plugin. I'll always say that you can use GHydra, Hail Hydra, if you want to. The steps that we take here today are going to be pretty much the same, just the interface will be different if you want to use a free decompiler instead of the Xrefs one. But we'll be using the Xrefs one, so what we're going to do here is the first thing is produce a C file here. And what that does is that forces IDA to decompile all of the functions. There we go, all the functions in the binary. Because if we don't do that, what happens is IDA will just decompile each function as you enter it. And that could lead to some issues with bad function prototypes, or maybe some of the arguments not being defined properly until you enter a function. So by creating that C file, we basically just force IDA to decompile everything, and then we know we're good to go. There was a video we did on this a while back talking about IDA microcode and how sometimes if you don't do that, it can mess things up. Okay, so now that we have it decompiled, we'll just do an F5 here to bring up our pseudocode window. I like to have them in a split view here, and I'll move the split view over a little bit more. And I'm going to right click and do a text view here because I'd like to see the assembly in a text view. So right now we're in the DLL entry point and there's nothing really in here. We have to take a look at the exports. So we can see nothing much in that export. And, oh, we didn't synchronize here. To synchronize with our disassembly view here. So we can take a look at the code in the export, but really what we want to focus on in this stream is we want to focus on decrypting the configuration file in Hancitor. And the best way to do that is to look for, I mean, you could do, if you followed our last stream, we basically went linearly through the functions until we found what looked like a decryption function. What you can do, and we're going to show in this case, is you can actually just look for data in the encrypted data in the binary itself, and based on that, you can sort of you can speed up this process a little bit by not having to look through all the code. So we can see here we've already found what looks like a big chunk of blob of data. I'll make this a little bigger so you guys can see. So you can see all I was doing was just scrolling through. I moved my cursor over to the blue areas where there's code. So I moved it over to where there's undefined or data that's unknown to IDA. And then I just started scrolling through. And you can also do this a different way. You can see here's the PE sections. So you could also just open up your PE sections and you could look, text is where the code is. So we could just look at these other sections and see, is there anything interesting in these sections here? You look at the data section and you can see this, to me, looks like a bunch of encrypted code, right? Do this. So it looks like something interesting, right? That's a string. It looks like maybe there's some strings or something in there. It's not null bytes. It's not a bunch of D words. It looks too random for that. But it's definitely something, and it has references in the code. That's what these mean. When you see a label here, it means this chunk of data is referenced somewhere in the code. So what we can do now is we just right-click and show us the Xrefs. Where's our jump to Xrefs? And so there's only one cross-reference to that piece of data. So let's jump there now. And if we look in our, so we can see here in our assembly here, that offset to that data is being pushed with some sort of number. And what's this? Oh, another reference in memory. And that's all being sent to this function here. Oh, and well, here we go, folks. So walk with me here. We open that function, and what do we have? We have a decrypt call, which is a Windows API call, which can be used to decrypt data. So it looks like we've already, a couple minutes in here, we've already found an interesting piece of data that's encrypted, and it's being decrypted at runtime. So this is a good place to start looking. Again, if you if you weren't having any success finding large, interesting pieces of data in the PE file, you could always go linearly. You could start at those exports and start working your way through the code and reversing it. This is just, after looking at a lot of malware, this is faster if you just want to get the config out. Usually they have to hide that config somewhere. It'll be in a resource, or it'll be in one of the PE data sections. Like that's basically, that's all the options that you have if you're trying to hide a config somewhere. So basically here we go. Let's figure out how this thing is encrypted and how it's being decrypted, and see if we can't reproduce that in Python. Now, before we go any further, I picked this sample because somebody from one of our Patreons was asking for more Python scripting tutorials. And I think this one is kind of interesting because we get to do a little bit more than just a basic XOR decryption here. So as we work through the crypto here, as we work through the decryption routine, you'll see that there's something a little bit more interesting that we get to do in Python here. So the first thing we want to do is pop open our browser here, because I don't know these APIs off by hand, right? Off by heart. So what I'm going to do is I'm going to look them up. And this is a big part of my reverse engineering, is going to the MSDN documents and figuring out what the heck these things do. So one thing to keep in mind when you have Windows crypto is it's not a simple call to decrypt this data. The way that it works is they use these crypto providers, or this is I guess, is that the right way to say it? I think you'd say it they call it a cryptographic service provider. They basically set up the context for the cryptography with a couple API calls, and then they use that context to then do the decryption. So you'll never see a key and a piece of data being passed to a function. What you'll more likely see is some context being set up for the crypto, and then the decryption function being called. So that's what we can see here. We can see that they're setting up the crypto context here. They're doing a crypt create hash. So what we can do when we see something like this, actually I'll show you. I know this off by heart, but it's better just to show you in case you don't remember. We can look up this function here. And see the arguments. So the first argument is the CSP, so that's the context for the decryption. But the second argument, this ALG-ID, stands for an algorithm ID. And this is what we call like an enum or a macro value, where when you're writing the code, you would use the macro name for it. But once it's compiled, it turns into just a number, right? And then that number is interpreted by the function. So what we need to do is we need to translate that number back into something that we can understand. So we want to know what is the actual algorithm being used. And the way to do this is you could either right click and do enums, or you could press the M key. So if we do enums, we want to search for them, and we can see that there is a whole bunch of different ones that match, but because we're creating a hash, the one that makes the most sense is a SHA or SHA-1, basically. So we know that they're doing a SHA-1 hash here, and that's basically how you reverse enums back into their original text format. Now, these enums are built into IDA. Sometimes if you're using third-party libraries, you won't have the enums for it, and you're going to have to look up what that enum table is. So you can see here, yeah, here you go. So here's all the values for the enums, and you might have to import those into IDA as an enum if it's not already in IDA. But of course, you know, IDA helpfully has the Windows ones already in it, so we could just right-click and look up the value here. So we know we're creating a SHA-1 hash, and we also know that we're deriving a key from the hash, I believe. So that's, yeah, we're still in the same crypto context. So remember when you have, oh, here's our p hash. So what's the best way to explain this? Yeah, okay, here we go. So once we've created the context for the hashing algorithm, then we actually have to pass in the data for the hashing algorithm. So what we're trying to do here is we're trying to figure out what we're actually taking a hash of. So we're taking a hash of the second argument here, the data that's passed as the second argument to this function. So that's going to be turned into a SHA-1 hash. So that's something we need to keep in mind. And maybe now is a good time to open up our CyberChef here and just make sure that we we'll do a SHA-1. Make sure that we have this stuff set up so we can test our hypothesis. Once we figure out how this decryption works, we can test it in CyberChef, and then once we figure that out, we can replicate it in Python. So let's put in the SHA-1 hash, and let's figure out what that data is that's being passed as the second argument, well, third argument, but second piece of data to this function. And actually, let's press N, and we'll rename this function as malware decrypt data. All right, let's do an Xref to this. And so what is the second thing they pass in? Well, it's this, and the length is 8 bytes. So let's just do a copy here, copy hex, thanks to our IDA plugin. Paste this in here, and we're gonna have to convert that from hex. So from hex, just like that. Okay, so this is the first thing they're doing in that decryption function. They're taking that data that's passed in as an argument. They are then doing a SHA-1 hash of it, and that's the output here. So what's the next thing they do? Next thing they do, oh, I'm hiding something? Yeah, I'm hiding some arguments. Okay, what I'll do is I will just make this a little bit smaller here for you guys. Is that a little bit better? Yeah, so hopefully, here, I'll just move this over a little. There we go. So now we can see what's going on here. Okay, yeah, sorry for that. Sometimes I forget where the camera is. Okay, so once we have our hash, we use that to derive a key, And the interesting thing about the Windows crypto APIs is that when you're deriving your key, you're basically doing it behind the scenes in the Windows API context. So the algorithm that you want to derive the key for is actually passed in this function here. And of course, if you didn't remember that, if you just wanted to look it up, we could look it up here again on MSDN. Right? So the second argument here is the algorithm for the crypto call that you're going to make. And so what we can do here is we can use the same trick we did before, where we right-click on our value here. We use the enum to convert it back into its original macro value or its enum value. So we can see there's only one hit here for RC4. So we now know that we're going to be working with an RC4 decryption algorithm. So there we go. This is like, it's much easier when you use the Windows APIs because you don't really have to reverse engineer any code. You just have to figure out what the arguments are that are being passed to the functions. And then you can, you basically have the answer. So it's, so here we go. So we know that they're going to take that data from the second argument here, or I guess the third argument, but second piece of data that's passed to the decryption function, and they're going to take a SHA-1 hash of it, and then they're going to use the SHA-1 hash as a key for an RC4 decryption. And it looks like the data they're going to decrypt is the first argument that they pass into the function. So there's one extra thing that, yeah, actually I saw in the chat there's an offline version of MSDN that integrates into IDA. Yeah, it's actually kind of cool. There's a way you can do these lookups automatically in the from IDA itself, but I don't have that set up right now. I might set that up for the next stream because it makes it a little bit easier. I find it kind of noisy because it has like a pop-up thing, so I don't really like that, but I'll set it up just to show you guys how it works, maybe for the next stream. Okay, so now we want to get to, actually, sorry, there's one extra thing here in the derived key. So we're not going to be using the full output from the SHA-1 hash. And the reason why I know that is because I've seen this API call a couple times, but basically if you didn't know that, you'd have to look at the arguments to that crypt derived key function. And you could see here in the flags here, they're basically talking about what type. So I guess there's two things. So the flags do two things. They have they define what type of key. If there's some extra special parameters for the key, you can use flags here. But they also let's see where this is. The key size representing the length of the key modulus in bits is set with the upper 16 bytes of the parameter. So this is like some classic Microsoft insanity where they're passing two pieces of information in one argument. And so they use the top word of the D word argument to pass the size of the key, and they use the bottom word to, or the least significant word to pass these flags. So if you miss that, then you wouldn't know that the key size isn't the full SHA-1 hash. We have to figure out what is the key size. So let's come in here and we'll take a look at this value here. Now, because it's in hex, it's kind of easy to split the D words, or to split the D word into two words. We can just grab like the bottom two bytes are the lower word, and then the upper 2 bytes, the null byte for this isn't shown, so it's 0028. So that's the length in bits of the key. And of course, if we, so 28 in bits, so that's 0x28 divided by 8 gives us 5 bytes. So the key is only going to be the first 5 bytes of that SHA-1 hash. So that's basically a little trick here. If you aren't familiar with the crypt derived key function, you could make a mistake and think that you're doing RC4 with the entire hash, but you're not. You're just using the least significant, most like 5 bytes of the hash. Or the first 5 bytes of the hash. Yeah, anyway, so now that we know that, we can go and see if we can do some decryption here. So we can find out what if we do an Xref to this argument here, find out what the data is that they're passing in. So let's double click on this. What is that? It's actually being copied from this piece of memory. Oh, interesting. So in the data section of the binary, you have the key, first 8 bytes, and then you have the data afterwards. So it looks like it's 2 and 3 zeros hex is the size of this. And so if we scroll down here, it's going to be kind of big, I think. No jokes about the size of this data. Keep scrolling. Oh my god. Oh my god. Now there's probably some of you screaming in the chat that I could just do a copy from the Python command line with that size. That's true. I could. I probably should have. But now I've committed to scrolling, so we're going to have to keep scrolling. Oh my god, this is huge. All right. Come on. Come on. Where's the end of this? I can't believe. Oh, there we go. Okay. All right. Okay. There's the end. All right. So we'll shift, click, right click, copy hex. And in our CyberChef here, we're going to actually open a second CyberChef because we need to do the decryption and the key setup separate. So here we're going to paste in that data. We're going to do RC4 decryption. And the input is going to be hex. And the passphrase is also going to be hex. And it's going to be the first 5 bytes here. So 1, actually, it's kind of cool. You can see in the length here is 10. So 10 is actually hex 5 bytes. So if we grab 10, see, come in here, paste this in. Hey, look at that. Decrypted. There we go, right? So we have some data here, and then what looks like some C2s, and then a whole truckload of null bytes. All right, so the first part of this is done. We did very, very little reverse engineering. As you can see, some of these things are very easy to decrypt because they follow a similar pattern to other malware, right? You have a decrypted blob in one of the data sections in the P file. It's referenced once by a single function in the code. You go look at that function, you figure out how it's actually manipulating that data. There's your decryption algorithm. So there we go. The next step is, I think, probably the more interesting for some of you, which is how do we write this out in a static config extractor in Python? What's the best way to do this? Now, in our last stream, what we did was we decided that they were probably going to be keeping this pattern the same in the data section. So we basically use the fact that there is a set pattern in the data section to extract that without having to look at any of the code. In this case, I'm going to do it a little bit different. I think you could probably do that same approach here, but the approach I'm going to use allows us to do a little bit more interesting stuff in Python, and it's actually a little bit more precise way of extracting configs, which you may have to use in samples where this pattern doesn't exist in a data section in the P file. And for that, what we're going to do is we're going to find this assembly code. So we're going to look at the best way to do this is to show us in options, general, show 8 opcodes. So now what we have here is we have the opcodes, which are going to, yeah, I can see, you can choose how many lines to scroll in the Windows setting. Yeah, I know. I feel like me scrolling through giant sections of data is going to be a recurring theme on this stream. I always start and then it's longer than I think, and then I'm committed and I just have to keep scrolling. I apologize. I'll try and find a better way to do this. Okay, anyway, so we've turned on show opcodes, and this is really useful. This is the view that I use for, say, writing YAR rules, and it's the view I use for writing these types of config extractors that we're going to write today. The reason why is because these hex bytes are the actual bytes that exist in the file, and they match up with this assembly. So what we can do is we can look at this assembly and say, this looks pretty unique, right? We're pushing a size and then an offset to somewhere in the P file, and then another size and an offset to somewhere in the P file, and then we're calling a function. So these bytes here are going to be pretty unique within this binary. So what we can do is we can use that against the malware developer, and we can use that as like a key to trigger in, our config extractor and identify this code without actually having to disassemble the binary in our config extractor. And one thing to note, we're making an assumption here, and I think it's good to call this assumption out so that you guys know why I'm confident doing this. If we look at this config, if we look at the size of the config, it's 2 and 3 zeros hex long. It's ginormous. But if we look at the data in the config, they only use a little part at the beginning and the rest is null bytes. So what's going on here? What does this mean? Well, I've seen this a lot in malware, and what this usually means is the binary is developed as a template, and they give a certain size to put the config in, and the config can be changed external to the binary. So you can basically just swap anything you want into that config area and go from there. When you see something like this where you have a set size for the config and then a whole bunch of null bytes that aren't being used, it's usually a good tip that the developer has used this methodology. The malware developer has decided, I don't have to recompile this binary and change the size of the config with each new build. What I want to do is I just want to have the binary set. I'll give them lots of space to put the config in, and then I can change the config with each build without having to recompile the binary. So that's what this looks like. Anytime you see something like a giant config that's all null bytes, it's not being used, but the config size is hard-coded in the binary, that's always a good indication that that config is, the size is not dynamic. It's static, it's set in the compiled binary, and they just change the data that's in the config each time they build a new version of Hancitor. So we're betting on that when we write our config extractor. That's the weakness in this that we're taking advantage of. Of course, the malware developer could see this stream and they could change it, but you have to think that they're doing this for a reason, right? They're doing it because they don't want to have to recompile the binary technique that's being used. So what does this mean? Well, it means that this size of the config is likely constant, and that means that these bytes here are likely constant. So we can use these as a key to find this little assembly location in memory. And I think the right thing to do now is to switch into our Python shell and show you exactly what I mean. So for our Python today, we're going to be using our lab notes, which is a Jupyter notebook that we host on GitHub. So we'll go into our documents here, Git and lab notes, and then we'll start our Jupyter lab. All right, and I will make this a little bit smaller so you guys can see. Minimize that window. All right, so hopefully the text is large enough for you guys to see. Let me know if you can't see this. And so we're going to create a new folder. We're going to call it Hancitor. In our Hancitor folder, we're going to create a new Python 3 notebook, and we're going to name this Hancitor. All right. And so now what we can do is we can start writing Python here. And I will save this notebook. I'll upload it to our GitHub, and the link is in the video description below. So you guys can go copy this later if you want and use it at home, go through and walk through the exercise by yourselves. So the first thing we want to do is we want to actually copy that binary into our Python environment here. And I'm also going to set up a few imports here. So we know we're going to be working with a PE file, so we're going to have to import PE file. We're going to have to import RE, which is the regex engine for Python, because we're going to do some regular expressions. we're going to be converting some data into numbers. So we're going to have to import struct. And of course, we are going to do that SHA-1 hash, so we need to import hashlib. All right, there we go. So we got our imports in here. Next thing we want to do is grab our file, our PE file as data. So we'll do data equals open as, let's see where this thing is. Have to find this in my folders here. Malware, Hancitor. All right. And we'll make this real string, paste that in, and then we want to do Hancitor.bin. Okay, we'll read it as binary, and we will read that file in. All right. Next thing we want to do is we want to create, we want to parse that data as a PE file so that we can access those sections and offsets within the context of PE, of the PE structure. So we'll do P equals PE file dot PE and the data equals data. And again, any of this syntax, if you're unsure of it, you can look it up. These are all libraries. I think the only one that you need to install is PE file, so you'd have to do a pip install PE file. The rest of them are native libraries in Python, so you have access to them. So what do we want to do? We want to find this. It's going to be hard to do this here. There we go. So we want to find the call here to this function because it has in it the reference to the key, and it has the reference to the data. Well, actually, that's not the data offset. It just has a reference to the key. And again, that's this value right here is the offset to where the key is stored in the PE file. So what we can do is we can grab these bytes here and what do we want to do? Yeah, just grab these ones, I think. Just these ones here. And we'll copy as hex. We'll come into our node here, and this is our key. So we'll paste this in here, and we're just going to clean it up a little bit. So we have to note that it's hex. I'm sure there's a better way to do this, but I'm showing you guys the way that I do it, so I won't skip any steps for you here. Okay. So that's our hex bytes, and of course the location in memory might change, so we need to null out some of these bytes. So let's go back to our IDA here. So we know that, so oh yeah, I should also mention, these opcodes, they represent an opcode, an operation, and an operand. So they represent both the instruction and the operand, which is the argument that you're passing to the instruction. Now, I just know off by heart that like 6A is the push part and 08 is the value. Now, you don't have to know that. You can just look these up, look up these opcodes. You can also just match the value here with the value you're seeing here. So if I, for example, in this one, we know that the 2 and 3 zeros hex is this D word here, and we know that the push instruction is this, simply because this value matches up with the 2 and 3 zeros hex here. So that's basically it. So what we need to do is we need to actually nop out the pointer to this data here. So that's 4 bytes after the 6-8. We want to actually remove those from our regular expression. We're going to use a regular expression to find this in the PE file. And we want to remove it because this could change, obviously, right? They could put that config anywhere. But what we're banking on them not changing is the fact that the length is going to be 2 and 3 zeros, right? We're expecting that to be constant because, again, we're betting that they built this and then they just swap out that config so that they don't have to change these values. We also know the key size could change, so that 08, that could change. It could be a different size. So why don't we make this a wildcard, and why don't we make these 4 bytes here also a wildcard? So let's pop over to our expression here. So the 08 is going to be a wildcard, and in regular expressions, it's just a wildcard, it's just a dot. And after the 68, the next 4 bytes, 1, 2, 3, 4, are going to be wildcards. 1, 2, 3, 4. And I'm going to do something in our regular expression here. I'm going to create what's called a capture group by putting brackets around these guys. And the capture group means that I can actually index the values that are in here once I've found a regular expression match. So that's all I'm doing here. You might need to look up a little bit about how Python regular expressions work. And there's actually a really nice, I should clear this out. This is kind of wonky. A really nice site called Regex 101. Which allows you to build and debug regular expressions live. You can choose Python here. It's super helpful, and I use the heck out of it for everything, basically. Any regular expression I'm doing, I will try it out here in Regex 101 first, and then I'll leave. And then I'll go and basically use it in my code. So here's our regex. Now what we want to do is we want to test out the regex. So, let's actually stay in here. We'll do m equals, so m is for our match, equals re.search, and we'll search for the key in our data. And then let's say if m is not equal to none, then print the first capture group. So print, and what's in the first capture group? It is the length of the key. So this is key length. And so that will be m.group1. And actually, why don't we print this as thank you chat, search. Thanks guys, you can catch all my typos. If you see a typo, throw it into the comments so I can fix it. Also, I put a typo here. I'm terrible at typing, especially live. Oh my god, can you make a comprehensive 5-minute video on how to unpack VM Protect? Yeah, bro, yeah. Okay, sorry, sidetracked. So actually we'll just print this out as bytes for now. So I'll convert those back into a integer or a number in a bit. But I just want to print these out to show you guys this actually works first. So let's grab this and we'll print the key offset, or key address, sorry. And that is the capture group 2. So let's see if this works. Oh, unexpected indent. Okay, so is that the key length binary? Byte 08, I think it is. Right, byte 08, yeah. And then 10, 50, 56, 00. 10 PV 50, 56, 00. So we were actually able to find, sorry guys, I'm totally sidetracked by the chat here. Ask Duncan to unpack VM Protect for you. He should be able to do it with x64 debug, right? Okay, I'm sorry guys. Okay, so we found the data that we want in the PE file. Next thing we want to do is want to convert these into integer values so we can actually use them. And for that, we're going to use struct. I think I've shown in some other videos how to use struct, but I'll just go over it here quickly. If you have a value that's in bytes and you want to convert them back into integer, you can use struct unpack and basically do that conversion. So the way to do that is struct.unpack, and you can look this up for the symbols, but B is for bytes, so we know that the length is just a single byte here. So the length is going to be M group 1, and we grab the first, it comes out as an array, so we'll just grab the first byte of it, And then, so that's 8. And then if we want to do the struct unpack of the key address, so the address is stored in little endian, and that's what this little less than I bracket means, or capital I means. It's little endian format. Again, you could just look these up in the docs for struct, and you can see what I'm talking about here. Okay, so that's the address in binary. That's not good. Let's do it in hex. Okay, so that's the address in hex of the key, and let's see if that's right in IDA. Yeah, there we go. Perfect. So with that, a little bit of regexing, and we now have located the key, and we know the key length in our file. So all we need to do now is copy out. We know the key length. We know that the data comes right after the key. So we just need to copy out the data in the key, and then do a SHA-1 to turn that into the key that's passed to the RC4 decryption, and then RC4 decrypt. So let's write that up now. Let's actually turn this into, instead of just showing us the values, let's actually turn these into some values we can use. So we'll do key, whoops, that's not good. Here, key len equals this, and the key address equals this. And of course, remove that extra bracket. And then what we want to do is we have to talk a little bit about how that address translates into an offset in the file, because we actually want to find that data. And this is where PE file comes in to help us. So what we can do is we can convert this address into an RVA by subtracting the base address. The regular expression should be in raw bytes. Yeah, yes, you can do that. It doesn't make a big difference here, but yeah, you should probably do like the raw bytes. Yeah, but yeah. Otherwise, you can run into trouble with the characters. Yeah, exactly. So some of these can be control characters. Yeah, that's a good point. Yeah, that's a good point. There you go. So this is just, all this does is just tells you that the string itself is a raw string, so it tells you not to interpret these as control characters. Anyway, thanks in the chat for that. So now that we have the address, we want to convert that into an offset. I see also in the chat, how can you use Yara instead of regex? Yes, but this is much better. If you have to do a lot of these, this is a better setup. Yara works better if you have a system set up where the Yara is going to then it's where you have like basically a Yara engine that's spitting out this data into a config extractor. If you're writing one-offs, the regexes are a little bit faster, a little bit better. You don't have to import Yara and worry about like the Yara binary being installed. There's a lot of extra dependencies and stuff that come along with Yara. If you're interested in how to use Yara to do this sort of thing, you can look at the Cape sandbox. They actually have a good example of how to do this with Yara. And you can also look at, there's I can't remember, the Japan Cert. I can't remember the name of their sandbox, but they have like JP Cert has a sandbox that does this with Yara as well. So they have like Yara-based config extractors. But for this, we're going to use regular expressions. All right. Again, sidetracked. So what we want to do is we want to convert this address into an offset in the file so we can actually grab it out of our data stream. And to do that, we have to use two pieces of information from the PE file. So the first thing we want to do is we want to turn this into a relative virtual address by subtracting the base address of the PE file. And then we can convert the relative virtual address into an offset in the file. So let's do key RVA equals key address minus PE dot, I had this saved, optional header. Yeah, optional header image base address. I always forget these and have to look them up, so to save a little time, I wrote them down. Yeah, CAPE is a huge learning curve. I mean, kind of. It's like you're basically relying on a lot of mechanics that are built under the hood, like a black box, to do your extraction for you. If you want to get nitty and gritty and really understand what we're doing, this sort of approach is going to be better. Just for learning, it's going to be better to do it this way. So we're going to do key address minus the optional header with the image base. So that subtracts the image base for the PE file from this address here, and that gives us an RVA. And then we can use this nice function in PE file to convert the offset into the RVA, sorry, into a file offset. So you can do get offset from RVA. It's built into the PE file library, and then we get our key offset. And then the key offset is actually the real offset to where that data is in the binary. So we can now use this to get our key data because we know it's data at key offset. And we know the length is the length that we got here. Okay, so let's actually print that out. And make sure we got this right. Q89AD. Does that look like this? Yeah, 89AD. Yeah, so we've grabbed this data now out of the file using a regular expression and then converting that address that we found, oops, that address that we found here, converting that into an RVA, then converting it into an offset so we can actually index it in our file, and then copying it out. So after all that, we have the key data. What's the next thing we want to do? Well, let's get that actual data, the config data. So the config data is actually easier because we already have a reference to where it is in the file from the key, because we know it follows right after the key. So it's data at the end of the key plus, and the length of it is 0x2 and 3 zeros, I think. Let's just double check that. What was the length of it? 2 and 3 zeros. Yep. There we go. So now we have the config data and the key data. So now what we need to do is we need to convert the key into a SHA-1 hash. We need to take the first 5 bytes of that, and then we need to do an RC4 decryption of this config data with that key. So this is actually pretty straightforward now. The hardest part of this was to create our regular expression to actually find that data in the file. So the rest of it is pretty simple, like straightforward coding. So what we'll do is we will do create a hash from the hashlib. So we'll do hashlib.sha1, and then we will turn that into m.update. Again, if you aren't familiar with the syntax, you can just look up hashlib, look up the docs for it. This is how you hash a file. So you basically do an update and then you print the digest of it. So we're going to do key data is what we're hashing, and then the key is equal to m.digest. And that is just a way to print out the hash of that data. And we want to take the first 5 bytes, remember, because we found based on that argument that they take the first 5 bytes. So let's take the first 5 bytes. Okay, so we have our key. Next thing we want to do is we want to do some RC4 decryption. Now I'm not going to write out the whole RC4 decryption algorithm because we've already done that. And we've already done it. See, this is the helpful part of having some lab notes. I remember in Warzone, they had an RC4 decryption. So let's just copy these bytes out. All right, so now we have RC4 decrypt, and we have our key, and we have our data. So let's do some decryption here. out equals RC4 crypt. The first thing is the data, so that is config data. Oops. And the next thing is the key that we just extracted here. All right, actually, instead of printing it out, I'll just print it to the screen here. Hey, look at that. So we have extracted the config here in Python. All we have to do now is clean this up a little bit. So that's it. We're at 1 o'clock. That is how to basically do this quick reverse engineering, quick triage to find where the config is, and then unpack it, or basically reproduce that in Python and create a Python extractor. If you stick around, I'll show you guys how to clean this up a little bit and make some sense out of it. But if you just wanted to be, just want to figure out how to write a config extractor for Hancitor, there it is. We're all done. So let's clean this up, and then I'll stick around on stream and answer any question you guys have. I saw there was like a ton of stuff in the chat as I was typing, so I can go back and take a look at that as well. So just to clean this up, we want to find out what this value is. So obviously these are the C2 URLs, but there's this weird value here at the beginning. And I think the best way to, oh, somebody's asking where will this be up? So we just post these live streams on our YouTube channel. So once we're done, we just upload the recording to the YouTube channel and make it public. So you can go back and take a look at it if you want. And again, in the description of the video below, once it's posted, we'll have our link to our lab notes and the sample if you guys want to play along from home. Okay, what is this value? Let's go back to our IDA, and I'll show you kind of a fun way to do this. So let's make our disassembly here a little bit bigger. So we have to name this as malware decrypt config. And let's do cross references and see where this config is used. Okay, so when you decrypt the config, this is the config here. Do a little bit more reversing. And we can see, we can figure out what that value is immediately, because if we look at this string here, this is actually the URL path that Hancitor sends to its command and control server, and they build it using a format string. So basically format string, it's like a way to convert these values into strings. And so we can see the first, they're noted by the %. So the first argument is this GUID, and then the second argument that's passed in is the build, and that build is the config that we've just decrypted. Now with format string, the first null byte is going to be the end of the string. So for them, it doesn't really matter that that there's all these null bytes and other stuff after here. When you use the format string, you basically just grab this value up into the first null byte. So this right here, we now know is the build ID for the bot, just by looking at this string here. So the malware developers have helped us out a little bit in figuring out what this config is. So that's the build. So why don't we parse that out first, and we'll try and make this a little bit cleaner in our config extractor. So this is the config, and out of the config, we want to grab the build ID. And so if we split the config on null bytes and just take the first bit, that should be the build ID. So we'll do config.split on null bytes, and we'll grab the first one. So that's the build ID. And then we want to grab the URLs, which are the only other piece of data in this whole in the whole decrypted config. The only other piece of data is the URLs. So we can do kind of a lazy parsing of the URL path of the config, sorry, by just saying any other data that's not the first string in there, that's not null bytes, grab that. So let's do C2 string equals blank binary. And then what we're going to do is we're going to say for s in config.split. So we're splitting it up on those null bytes, and we're actually going to take after the first one. So we'll do anything after the first string, because we know the first string is the build ID. So anything after the first string, if s is not equal to null byte, is not equal to an empty string, because of course when you split a whole bunch of null bytes in a row, you're going to end up with a whole bunch of empty strings. So if it's not an empty string, then it must be the C2 string. So the first one is going to be the C2 string. And we want to break out of this. All right, and then what we can do next is we can split that C2 string up. Actually, let's just print it out. So we'll just do print the build is %s, and the build that we extracted here is this. And then we want to print the C2 %s, and we'll grab the C2 string here. All right, so we have the C2 string. I can see Dragon saying ++. No, we don't actually want to add it. We just want to grab the first C2 string. This is just a janky one. This is just a janky way to extract it. There's only one blob of C2 strings, so we don't need to do that sort of plus equals s. We're just going to break on the very first time we find it. Again, there's other ways, better ways to parse this out, but this is just a lazy way to do it. We can see our C2 list has separated by these pipe characters. So instead of doing this, why don't we make a C2 list out of this? So we'll do a C2 list equals C2 string dot split on our pipe. And so now we have a C2 list, and then what we'll do is we'll just do a while loop for C2 in C2 list. We will print out our C2. There we go. Oh, and there's an empty string. So let's say if it's empty, if C2 not equal to an empty string. Print it out. Oops. There we go. Okay, done. Yeah, I can see some people making fun of my Python. I think I mentioned this before. I'm basically, I do actually write a lot of stuff in Python. In fact, most of my day job is writing code and not reversing, which is really embarrassing. But what my crutch here is the fact that I've written stuff in Python 2.7 forever, and it's taking a really long time to figure out how to convert to like the new standard of Python 3. I know we're not supposed to be using this notation. I know it, but it's just like when I'm on stream and I'm trying to do it quickly, I still do it the original way. You'll see. Stick around for more streams and you'll see I'll get better at it. But yeah, I also I use Flake 8 like that delinter on all my code at work. So I do actually write decent, PEB conforming Python at work. If you're gonna give me a job, don't go by this. I do know how to do it. It's just when I'm, when it's time to do it, I still have all these old habits. Okay, so with that is the end of our little tutorial here. What I'm going to do is I'm going to stick around. I'll throw this up to plug our, actually I'll minimize that. I'll throw this up to plug our Patreon while I answer questions. If you like these and you want me to do these instead of what pays the bills, sub on Patreon. And I'll stick around for a couple minutes and answer any questions you guys have. So dump your questions in the chat and I'll try to answer as many as I can. I'll stick around for maybe 15 minutes or so, or until the questions end. Yeah, so again, just a reminder, I will upload that notebook to our OALabs GitHub, and you guys can download it and pull out the Python code and use it yourself. So if you guys want to work through that, if you want to copy the code and use it, just head over there like a couple minutes after the stream. I'll upload it and it'll be there. F strings are faster. What are F strings? I'm gonna have to Google that. That's something I'm gonna have to look into. Amanda Bynes in the chat. Bynes cybersecurity. Yeah. Rust is cool. Nah, I mean, so the reason why I like Python for this kind of stuff is because it's kind of self-documenting. Don't throw a book at me. I know that's like no developer should ever say my code is self-documenting, but I like the way that this can kind of be read like a language. Whereas if you're coding in C or C++, you have to do a lot of extra boilerplate that can sometimes hide these like really plain algorithms. So it's always a trade-off. But that's why I think a lot of reversers use Python. It's just because it's a little easier to see what's going on. And of course you can like script stuff and then you can turn it into like basically a production ready code from a script. So it's kind of nice in that way as well. What else do we have in the chat? If you want merch, yeah, buy that merch, right? Paul Brothers, buy that merch. Go and click on the mugs and stuff below the stream. Hopefully it should be showing up somewhere. And you can buy a mug, support us. Let us know if you want to see other designs too. Oh, also I should plug our Discord. In the description of the video below, you can click, there's a link to Discord. Come on there, we're hanging out all the time. And if you have questions after the stream, you can ask there. We're always happy to jump in and chat with you guys. New to malware analysis, guide me first few steps. I would say this is actually a good sample to start with. If you want to just kind of start poking around in IDA, go download the sample and see if you can replicate what we've done today. Try and do it, and you can ask for, if you get stuck, ask in the Discord. Join the Discord and ask, and we'll try and help you. Take a moment to say thank you. Oh, thanks, guys. Yeah, I appreciate the support. Again, this is like. This is not my job. So the more support you give me, the more enthusiastic I am about doing this stuff. So thanks very much. All the nice comments and the little fun emojis and stuff you guys send me, it all helps me motivate me to keep doing this. Duncan, production ready until you need to scale. Bro, we can process the whole VT feed on Python and it's cheap. Python does scale. It's fast as frig if you know what you're doing. Fight me, Duncan. Actually, in the chat, you guys big up Duncan and see if he'll come on stream and show us some x64 debug tricks. I think that would be super fun. Don't really bug him, actually. He does a lot of really good work. But it would be nice if we could do an x64 debug stream where we sort of learn new things about that monster. Please never stop. Yeah, I mean, we're not going to stop doing this. We've been doing it for 5 years. We may not stream as often, depending on the kind of support we get, but if you guys support us, we will keep these streams going. Any other questions here? Put them in the chat. More questions. Kind of scrolling up. Yeah, I think for the next stream, I will try and set up my camera a little bit better, so that you guys can see the screen a little better. Yes, Duncan, do it. How often do you use pin tool for analysis? Actually, so if you are longtime subscribers, you might remember when we first released UNPACME, we did a little explainer video of all the stuff we messed up before we built UNPACME. And one of the things we did was we thought we could use pin tool as a DVI type, unpacker. And I don't use it. I don't use it because the development process for it is so aggravating. It's not that the tool itself isn't good. The pin tool is great, especially when you want to do like really precise style, you know, binary manipulation, debugging type stuff. It's actually good. The problem is it's not easy to do rapid prototyping with, just by the nature of how it's set up. It's really annoying. And so there's better, in my opinion, faster options out there. There's lots of like, free to DBI for like JavaScript if you like JavaScript, or you can just write like Python scripts and do like VM introspection and stuff like that if you want to get closer to what UNPACME is doing. You can do that. But pin tool, I don't know. There's like some cool stuff. If you want to try it out, Hasher8 has some awesome stuff on her GitHub. You can go check that out if you want to try out pin tool. But there's scar tissue here from us trying to use that at scale. It's just not, the development cycle for it is not great. Let's see what else we have here. Free way to do this in IDA. Yeah, so the one thing, Xrefs have been super nice about releasing like a decent free IDA version. So you can get its freeware. If you do the Flare VM install, it'll actually install that free version of IDA for you. The thing that it doesn't have is the decompiler, the Xrefs decompiler, which is expensive. I think it's like $3,000 or something. Like it's really pricey. I'm Canadian, so everything is like inflated for me, right? All these US prices are inflated. So if you want a decompiler, it's GHydra or you got to pay the money. That's basically all there is to it. Best 2 books for malware analysis. I don't really read books. These are for show. No, I'm joking. For malware analysis, I prefer videos, hands-on stuff, blogs. I feel like it's more current, more up to date. I think a lot of people who are into sort of like the book learning for malware analysis, I think there's like the 2 books that everybody uses. Was it Practical Malware Analysis? That's this guy here. This one, Practical Malware Analysis, and then there's what's the other one? I can't remember. Anyway, I would think I was gifted that at some point, and I just have it up there. Books for me are like a reference material, and right now I'm learning a lot about low-level like compiler stuff and for deobfuscation, and I find like books for that are great, but for learning a skill like reverse engineering, I wonder if the Dr. Fu blog is still up. Malware. Kind of dating myself here. Yeah, it is. Okay, this is like if you just want a free zero to hero, learn how to actually reverse engineer malware, learn how to analyze it. Check this out. This has been a guide. I don't know when this came out. It was like probably some of you weren't even born. But this is like this is better than any book. You're gonna learn stuff a lot faster, a lot better if you just check out some of these. There's also a couple resources I think we've posted in some of the comments before, other blogs that we think are good. But for learning how to do this, you really need to be sitting behind a computer, doing the work in IDA, doing the work in a debugger to learn it. Reading a book, it's probably not the best. And I know that these books have like examples and you're supposed to follow along, but in my opinion, this is better. What else do we have here? Are you from Toronto? No. No, I'm definitely not from Toronto. I live in Montreal. You guys can't tell from my accent? Yeah, I'm definitely not from Toronto. What else do we have here? People trying to scam these books. Yeah, actually, so a lot of these like books have been out forever. You can probably find free PDFs. You don't have to buy them. But do, support the authors. If you like the book, support the author, right? Yeah, what else we have here? Anything else? Are you planning to release courses for reverse engineering in the future? Yes, we are working on making a full course that'll be online for doing this kind of stuff, this sort of more reverse engineering oriented malware analysis. So there's lots of great courses on malware analysis, lots of analyst stuff. But what we're going to do is we're going to focus specifically on reverse engineering. But that's taking a while, and what we've done is we've set up this Patreon, and we're posting like modules from it to our Patreon. So it's just started. There isn't much on there, but as we build modules, we'll be posting it on here. So if you guys sub, you can just do the modules as they come out. We're not, no guarantees that we're going to be doing, 1 a week or anything crazy like that. But as we build content for the course, we'll be throwing it on Patreon. If you want to wait, then you can wait until we have like a full course, and then you can, sign up for the course. You heard a few of boots? Yeah, actually my Canadianism is saying A. I say A all the time. When I like edit my videos, it's totally wild. I have to I'm like, geez, do I really sound like that? Like I'm just saying A all the time. Then we open eye to A. Oh yeah, A. Yeah, anyway. Definitely Canadian. I live in Montreal. Actually, if Recon ever starts again, if you ever get stuff together and there's ever a Recon again, anyone who comes to Recon, I'm usually hanging out there, so you can say hi to me. CSP decryption routine, I'm not really sure what that stands for. Spell it out and I can maybe help with what it is. We're 20 past the hour, so get your questions in quick. I'm gonna end the stream soon, so we'll stick around a couple more minutes. Any burning questions, get them into the chat quick, and then I'm going to take off. Resources, courses for beginners. Yeah, there's more questions about how to start, reverse engineering malware. I think I mentioned this on the last. Hey, thanks, Amanda Vines. I think I mentioned this on the last channel, but I'll probably say this like every stream because we always get the same question. If you want to learn to be a malware analyst, there's lots of good resources out there. You can just Google for them. Yeah, Zero to Automated, love those guys. Awesome course, highly recommend it. Check them out. If you want to do reverse engineering of malware, the best way to do it is to pick a binary, pick one of these, pick the Hancitor DLL, and work through it piece by piece. Figure out, Google when you get stuck. And that's the best way, because then you're going to have an end goal in mind as you're working through it, rather than trying to learn all these separate skills and then put them together. It's going to be easier if you just have one goal and you focus on, and as you run into challenges with that goal, you then learn a little bit more about, what you don't know. You need to go and learn for each one. So the first one you do is going to be a long time, and then as you do more, it's going to be, as you do more, you'll get faster at it. But yeah, I do recommend Zero to Automated. I love those guys. They're great. And the course, I've heard nothing but good things about them, and also the support they give to the students. So yeah, definitely recommend. What else do we have here? Yeah, okay. I think that's it. So we're going to end our stream here, unless there's anything coming in on the chat. We're going to be taking off. So remember, sub if you want to see more of these. I'll be posting this video to your YouTube channel. If you missed any of it, you can go back and check it out. And the links for the sample and the notes will be in the description below. All right, until next time. See you later, guys.